Welcome to the Explainer. So we hear a ton about power, right? But what actually is it? I mean, depending on what you've been reading or watching today, your brain probably jumps in a million different directions. We throw the word around constantly, describing everything from star athletes to local politicians. But today, we're stripping away all that everyday slang and digging into what this word means at its absolute fundamental scientific core. It's honestly kind of fascinating to contrast our casual, everyday ideas of power with strict, no-nonsense physics. Normally, we're talking about political power, the government making things happen or preventing them. Or maybe people power, our collective ability to force a change. But in engineering, math, and physics, power has a rigidly specific, unbending definition. It is simply a measure of how quickly work can be done. It's not about influence, it is literally just effort over time.
And that brings us right to the heart of today's explainer: work, power, and efficiency. We're going to demystify the exact mathematical formulas that run our physical world. We'll look at how energy gets converted into work, how power dictates speed, and how efficiency puts a hard limit on our machines. By the time we wrap up, I promise you'll look at the tools in your garage in a totally different light. Here is our roadmap. 1. Defining work and power. 2. The formula for power. 3. Introducing simple machines. 4. The 3 lever classes. And 5. Calculating mechanical advantage. Let's jump right in.
Section 1. Defining work and power. Okay, to truly grasp work, we kind of need to look backward for a second. Surprisingly, the concept of work wasn't even a big area of focus for our old friend Sir Isaac Newton. The term work, at least how we use it in physics today, was actually introduced way back in 1826 by a French mathematician named Gaspard Gustave Coriolis. He defined it super simply: weight lifted through a height. And you can intuitively feel what he meant there, right? Hoisting a heavy weight up into the air demands effort. It demands work. It's basically just a transfer of energy. Let's get our units totally straight before we go any further. Force, that's measured in newtons. Distance is measured in meters. Now, when you multiply those two together to get work, you're looking at joules. And finally, power is measured in watts. Just keep these specific units tucked in the back of your mind as we move forward.
So here's our very first major equation. Work done equals force multiplied by distance. Picture yourself straining to shove a massive box across the floor. You have to apply a force to it to get it to move. But here is the catch, and it's a big one. Work is only actually done if the object moves in the direction of the force. If you spend all day pushing against a solid brick wall and it doesn't budge a single meter, well, in physics terms, your work done is absolutely zero. Zero. You absolutely need force, and you need a distance traveled.
Section 2. The formula for power. Now, the absolute key here is understanding the difference between joules and watts. Remember, work done is measured in joules, but power is the rate at which you're actually performing that work. The formula is power equals work done divided by time taken. So 1 watt, our standard unit of power, is simply 1 joule of work being done every single second. Think of it like this. If 2 people haul the exact same box up the exact same flight of stairs, they're doing the exact same amount of work in joules. But the person who sprints up the stairs and finishes first, they're generating way more power in watts. If you want a really easy way to organize this in your head, just picture a formula triangle. You've got joules sitting at the top and watts and time down at the bottom. This visual trick is brilliant for simplifying calculations. Want to find work? Just cover the J in your mind, and you're left with watts multiplied by time. Need to find power? Cover the W, and you get joules divided by time. It is literally a lifesaver for organizing the math without having to memorize a bunch of different algebraic rearrangements.
Section 3. Introducing simple machines.
Humanity has spent thousands of years trying to figure out how to basically cheat these exact math equations to make our lives easier, creating tools that cleverly manipulate force and distance. And it all boils down to just 6 fundamental simple machines. You've got the lever, the inclined plane, the wedge, the screw, the wheel and axle, and the pulley. Literally everything from a basic doorstop to a complex bicycle relies on these foundation blocks. But how do they actually help us? Well, they definitely don't magically reduce the total amount of work required. Remember, work is locked in as force times distance. Instead, these machines make jobs easier by doing one of 3 specific things. They either change the size of the force you need, they change the direction of the force you're applying, or they increase the speed or the distance an object is moved.
Section 4. The 3 lever classes.
Let's zoom in on the lever.
To really understand how it works, you have to know its anatomy. Every single lever out there, no matter how complicated it might look, is made up of exactly 3 parts. First, you have the resistance force, which is the load, the thing you're actually trying to move. Second is the effort force, which is the physical work you are putting into the lever. And third is the fulcrum. That's the fixed pivot point the lever rests and spins on. Now, you can rearrange those 3 pieces into 3 distinct classes, depending on where you put the effort, the resistance, and the fulcrum. A first-class lever, that's your classic seesaw, a crowbar, or a pair of scissors, where the fulcrum is right in the middle. A second-class lever puts the load in the middle. Think of a wheelbarrow, a bottle opener, or a nutcracker. And then a third-class lever puts the effort in the middle, stuff you use every single day like a broom, a shovel, or those barbecue tongs. Seriously, the pure physics of work and power are hiding right inside your kitchen drawers.
Section 5. Calculating mechanical advantage. Think about using a heavy-duty crowbar to pry something open. You might remember the principle of moments. To lift that load, the load and force on the left side of the pivot have to perfectly equal the load and force on the right. Because the crowbar has such a long handle, you can apply a really small effort force over a large distance to move a massive resistance over a tiny distance. We actually quantify this neat little trick using a super simple equation. With a lever, mechanical advantage is simply the load divided by the effort. And this concept maps perfectly onto an inclined plane, or a ramp. Say you've got a ramp that's 10 meters long, set up to bridge a 3-meter vertical gap. The math here is beautifully simple. You take the effort distance, that 10-meter ramp length, and divide it by the resistance distance, which is the straight 3-meter vertical drop you're overcoming. So 10 divided by 3 gives us a mechanical advantage of 3.3. Which literally means this ramp is multiplying your pushing strength by 3.3 times. How cool is that? Finally, let's look at a pulley system with a massive mechanical advantage of 10. Imagine a mover using this setup to hoist a heavy piano weighing 1,450 newtons up about 4 meters in the air. Because the mechanical advantage is 10, that mover only has to apply 1/10 of the effort force. 1,450 newtons divided by 10 means they only need to pull with 145 newtons of force. It's a total game changer. But keep in mind the trade-off is distance. To lift that piano 4 meters with a mechanical advantage of 10, our mover has to physically pull 40 meters of rope. You see, you never really get something for nothing in physics. In the real world, thanks to friction, no machine is ever 100% efficient. You're always going to lose a little bit of energy, so the work output will never perfectly match the work input. But by manipulating these variables, we make the impossible completely possible. Wow, we've covered a ton of ground today, right? From Gaspar Gustave Coriolis defining work all the way back in 1826 to calculating the mechanical advantage of a pulley hoisting a giant piano into the sky. Things like force, work, power, energy, mechanical advantage, they are not just abstract textbook numbers. They are the invisible rules governing every single movement in our physical world. So I want to leave you with this final provocative thought. The next time you push open a heavy door, snip something with scissors, or even just walk up a ramp, look a little closer. Where do you see mechanical advantage happening around you today? Thanks so much for joining me on this explainer, and keep looking for the physics hidden in your everyday life.